So you got 100? Even though you got one?
Yeah.
Oh, really? See, for this question, like finally I got all correct, right? So it actually just give me like 99%. I did everything correct, but eventually, but I didn't get the full correct because I got wrong doing like it, like 90.9.
I know last semester,
Uh-huh.
2.6.
What's that?
In last semester, in MIT 1.26.
1.26. Like calculus speed, like it.
If you have 5 wrong on the design, it's just options. If you have 5 tries.
Oh, really? So you think that it should be in the same system?
Probably. Like if you
I got you. Paper homework. You want us to give you the homework right now or later?
Yeah, someday your paper will are get from here.
What application do you use? School notes?
Yeah. What do you use? Notability?
Yeah. So why my note is very like ugly. So you handwriting or like system 10.2? Is it your handwriting? Oh, okay. That's why. Yeah, my handwriting is still I got it. Cool. quiz too. And
Oh yeah.
he has put the grade of quiz one. You know that?
Oh, yes.
Huh?
You do that.
Yeah. It's quite simple, quite easy. I didn't expect like that easy.
Yeah.
Oh, next week and you can email me. Also this section. Right here, name. Let me figure it out. That makes it better.
Sorry, you took, I didn't take a calculus B here. So when you took a calculus B, so usually like the last few questions will not appear on the exam. Right? They will not choose like very hard questions.
I mean, on the midterms and the finals, it depends on the professor.
It depends on Fisher. So it's like they have a three sessions. Like they will take all sessions with the same exam question or like individual approaches.
Each professor has a different exam.
If you couldn't submit paper homework, first paper homework today for any reason, then yeah, you can email me until tomorrow. I understand there are some confusion between some different types of homework. So if you couldn't submit it, then yeah, please email me. Yeah, so another paper homework about section 8.3 that was originally supposed to due today, but we postponed on our schedule for Labor Day. So it's due next Monday. And you can check the numbers of one for the syllabus. And there's quiz 2 next class. So Wednesday this week will about section 8.3 and 8.4. So the quiz will not have an estimate of the series using some type of test, but the questions will like determining the convergence and divergence using repetitive tests and comparison tests and absolute tests we will discuss today.
So basically, we have a three question, like
No, there are 2 questions.
2 questions
But usually these comparison tests
with interval.
everywhere. So test 2. Yeah. 2 questions. Oh yeah, and grader gave me the graded quiz 1, but I didn't bring today. I will give it that to you next class. Okay, any questions? Any questions about last lecture? Okay, so my plan is we finish section 8.4 today, and on Wednesday we will discuss some exercise problems from section 8.3 and 8.4. So I believe doing as many exercises as possible for these sections are important. So let's we finish section 8.4 today. Other convergence tests. So in this section, we will discuss a new type of series called alternating series. These series use terms. Alternatively positive and negative. Example, the harmonic series, but we alternate sign of terms. So 1 minus half plus a third minus the quarter plus and general term is a summation from n is equal to 1 to infinity. And sine negative 1 to the n minus 1 times 1 over n. So if you see this term negative 1 to the n minus 1, it changes sign whenever you add 1 to n. Another example is starting from negative half and 2/3 minus 3/4 of 4/5, and see the general term. So both numerator and denominator increase by 1, and it starts with 1 over 2. So it's negative 1 to the n times n over n plus 1. So these are examples of alternating series. So we will discuss the convergence and divergence of this series. Alternating series test. And we just abbreviate AST. For positive sequence Bn, if the alternating series summation n is equal to 1 to infinity and negative 1 to the n minus 1 times Bn. So if n is equal to 1, then you have positive side and B1. So it has B1 minus B2 plus B3 minus B4. And we assume that BI's are positive numbers. Satisfies. One, this term is decreasing for all n, and the limit is equal to 0. So if you combine these two, it's so this sequence is decreasing to 0. Then the series is convergent. Alternating sums of positive numbers. It's very powerful, sufficient condition for the convergence of alternating series. So let's use this to say the convergence of this series.
So b plus n, b sub n plus 1 is always negative number. So that's why it's a smaller than bn, right?
No, bn's are all positive. Bn's are positive, and we just take alternate sum.
But b sub n plus 1 will be negative, right?
No, I said it's positive. They are all positive.
They are all positive?
Yeah. Because we use the negative sign here, so you don't need to take extra negative number to minimize.
Oh.
So for yeah. So for this first example, the Pn is equal to 1 over n. And we take alternate signs of the series. And Bn is decreasing in n, and its limit will be n is decreasing to 0. So if you use alternating series test to this alternating sum, it converges. And compare to the fact that our original harmonic sum diverges. So if you take a summation of positive 1 over n, we show that it diverges. But if you take alternate infinite sum, then it converges by this alternating series test.
Compared to.
So let us see why this test works. It's pretty intuitive if we draw a picture.
So this one is a convergent, this one is a divergent.
Any question so far?
Yeah, I have a question. So you say that the 1 minus 1 over 2 is a divergent, right? This series divergent.
Sorry, what?
The bn equal to 1 minus n. This series is convergent, right?
This series converge.
And to compare the.
This diverge.
Oh,
we learned last week.
Okay.
So difference is here we.
It's the sign, the change
Yeah.
sign. Yeah.
We add all the positive number, but here we.
It's called harmonic series, right? Harmonic series.
It's harmonic series.
H.
So let's start with 0. And the first term, let us use the one-dimensional visualization, identifying the numbers with bi-infinite lines. And then by adding B1, we overlap by B1. And if you subtract B2 from B1, by this condition, length of B2 is smaller than length of B1, so we go to left, but it doesn't pass this line 0. So here minus B2 and this is partial sum, second partial sum, B1 minus B1 minus B2. And if you add B3 next, then B3 is less than B2. So again, so you can't pass this vertical line and stop before this vertical line. So here you plug this 3 and our Potter sum is here. B1 minus B2 plus B3. It's one more step. So we subtract B4. And again, B4 is less than B3. So it's offset before this dotted vertical line. And here is our fourth Potter sum. B1 minus B2 plus B3 minus B4. And so on. So what you can see zigzag between this interval and the length of the interval is getting
Smaller and
smaller and smaller and collapse to some points in the middle
2 0? 2 0?
to 0. No, some number between 0 and B1.
Oh, some number.
So it's like, yeah, so you convert it to some points. So this is a proof by picture. So, yeah. This is the sum of yeah. And let me label this figure. This is the figure 8.20 in the textbook. Yeah, so these two criteria are very simple to pass. Simple to pass whether the sequence is decreasing and whether the segment is equal to 0. It's easier than our previous integral tests. You should show the positive and decreasing of function. If you use. So, example 1 was about alternating. So example 1 is about 1 minus half plus a third minus 4. And we already discussed that and is decreasing to 0. So yeah, by F alternating series test, it converges. And the second example is consider alternating series. A little more complicated. 3n over 4n minus 1. So our general formula for this series is this term, but when we discuss this alternating series test, we are interested in positive number parts. So the n is usually defined as an absolute value of this alternating sequence.
Oh,
This is 3n over 4n minus 1. So we should test this decreasing property and convergence to 0. I'm gonna keep these statements, but yeah, that's right.
here.
denominator, I want to keep that. Students who slave.
So we always use the absolute sign to test, right?
Yeah.
Because when to keep positive.
Yes. So for these absolute alternating series tests, we should care about this positive part of alternating sum.
Okay. It's like to use a comparison, like AN and BN.
No, we don't use comparison test here.
Okay.
Yeah, this is just positive number, the absolute value of this alternating series. Let's try to apply alternating series test. So first, to show this decreasing property of this sequence, we can use the function fx divided by 3x over 4x minus 1, and take a derivative, then you get 4x minus 1 squared in the denominator. In numerator, you have derivative of numerator 3 times 4x minus 1 minus this times derivative denominator. So you have minus 3 over 4x minus 1 squared is negative. So Bn is f of n, and Fn is decreasing, so it's decreasing. So the first condition is okay. But the second condition is the limit of this Bn has to be 0. But here, limit of 3n over 4n minus 1. And if you see the highest degree of the polynomials in numerator and denominator, then you get 3/4, so it's not equal to 0. So it's very tempting to conclude here that there's something like since it doesn't satisfy condition of alternating series test averages. Is it correct?
Huh? What's that?
So is this conclusion correct?
Yeah, because doesn't equal to 0. Why? How can you know it's a decreasing? Is as long as smaller than 0, that there will be decreasing. The first condition. First condition.
So our function f is decreasing and Bn is f of n. So our sequence Bn is also decreasing.
Okay, so if it's smaller than 0, that will be decreasing, right?
So this means f n plus 1 is less than fn, and this is Bn, and this is Bn plus 1. So sequence is also increasing. This is incorrect. I mean, eventually it's diverges, but this reasoning is incorrect. Because
Is it incorrect?
this alternating series test tells you that if the series satisfies these two conditions, then it converges. But it
opposite.
doesn't say that if the series doesn't satisfy one condition, then it diverges. Can you understand the difference? So AS alternating series test tells if the two conditions are satisfied, then the series converges. But it doesn't say something like if it doesn't satisfy one of these two conditions, then it diverges.
It's like a P imply Q. Doesn't mean Q implies P, right?
It's related. So if you're familiar with this logic, P implies Q doesn't implies that not P implies not Q.
Oh yeah.
So
This
if it satisfies both, and then if it satisfies both, it's convergent. If it satisfies both, it's divergent.
Right?
If it satisfies both, it's convergent, and then if it only satisfies one, it's divergent.
You can't say that. Yeah, that is what I want.
So can we think about we only can think about it's a convergent, but we cannot think it's a
Right.
divergent.
The only thing you can conclude from AST is convergence. You can't say
Cannot say
divergence.
it's divergent.
So if we don't satisfy a condition, we basically can say that we can't say anything about the,
Convergence or divergence.
yeah, we basically just say we can't say anything about it.
Yeah, you can say about it. But I think this example is not good because this sequence actually diverges by almost the same reason. So sorry. I should prepare a better example because this example is from textbook, but actually if it doesn't satisfy the second condition, then it diverges. That's what we can say. Because there's a so we learn about a theorem that if series converge, then the sequence converges to zero. And it's not true, but what is true is P implies Q equivalent, not Q implies not P. So this tells you that if limit of a n is not equal to 0 or diverges, then the series diverges. So this was one of the theorems we learned 2 weeks ago. So here, oh yeah. So let's use this. So the limit of an, or an is -1 to n minus 1 times 3n over 4n minus 1. And we know that this fraction converges to 3/4. So this limit I mean, this sequence is oscillate. Between plus minus 3/4. Because the absolute value converges to 3/4 and we change the sign. So it should be something like 3/4 and negative 3/4 and our sequence converts like this way. But yeah, the important thing is this diverges. And by using this theorem, we can conclude that our alternating series diverges as well. Is it clear? So, yeah, I wanted to emphasize is you can say something like if one of these two conditions is not true, then the series is divergent. So for this alternating series test, we also have error bounds like we did for integral test, but this one is easier than integral test.
Error.
So here, if small s denotes the sum of our alternating series, minus 1 is the n, where the n's are positive, is the sum of alternating series satisfying these two conditions for this alternating series test. The n plus 1 is less than the n, and the limit of the n is equal to 0, so that we can use the alternating series test. So that series test. Then the error Rn, absolute value of error is equal to s minus n partial sum is less than or equal to n plus 1's term. So small s sub n is n partial sum. So in the integral test, what we had was this Rn, the difference between the actual sum and the partial sum is the area of infinitely many rectangles. And error was bounded by the integral of a function from n to infinity. For this alternating series, we only have this n plus 1's term.
What is the RME again?
R is s minus sn. is a residual sum. So
Remaining.
Sn is the first n partial sum, and if you take a difference between the actual sum and partial sum, then you have a residual
Like
series.
remaining, right?
Sorry?
Remaining, right?
Sorry, remain.
Remaining. So that's why it's
Yeah,
R.
you can
Right?
say it's remainder or residual. Yeah, expansion. So let us recall the figure which was here. Below GZ appears in the visualization of this series. So you have plus Bn here, then subtract Bn plus 1. But length of the arrow Bn plus 1 is shorter than the arrow of this Bn. Then our actual sum of this input series is in the middle of the zigzag. Limit of this alternating series is here. And so this Rn is a difference between this actual limit and the nth partial sum. And nth partial sum is the end of this arrow will be n. So this length is Rn. This value is partial sum Sn. And by the picture, you can see that this length of Rn is less than this arrow Pn plus 1. So from here, you can conclude that this length Rn is less than Pn plus 1. So yeah, so it's very simple upper bounds of this estimation of ultimate series. Any questions so far? Or estimate alternating series. Right to 3 decimal place. Remember that 0 factorial is equal to 1. So this sequence is well defined then for it is equal to 0. So let us check the conditions for alternating series class. Check condition. Alternating series test. First, here the n is an absolute value of this sequence, so it is 1 over n factorial. and its denominator is increasing when you increase n. So it's decreasing. And obviously it converges to 0 because the denominator was infinity. So we can use AST and we can say that this series converges. But you have to estimate to 3 decimal place. So let's use error bound. So S minus Sn surrender of Rn so less than Bn plus 1. Here Bn plus 1 is 1 over n plus 1 factorial. Just calculate first few factorials, then you can see that 8 factorial that 7 is 1 over n. 7 factorial is 1 over 5040. It is less than 5000. It's 0.0002. And the next is 1 over 8 factorial, which is 6. 6 factorial is 1 over 740, 720. It is greater than 1000, 0.001. So,
Do we?
so A6 is the least number satisfying our error term is bounded by 1 over n plus 1 factorial is less than 0.001. So that means to get 3 decimal place correct estimation, you only need to check the first 6 partial sum.
How can you decide it's a B7 first?
In technology,
Okay.
yeah, I skipped the
Experience?
calculation, but yeah, when you actually solve, you should calculate all these first few terms.
Okay.
Yeah, so you only need to check the first 6
First 6.
partial sum for this estimation. And 6 is 1 for n is equal to 0, and 1 for n is equal to 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 minus 120 plus 1720. It is 0.368 if you round off to the 3rd decimal place. And more interestingly, we will be able to show that this limit, the exact value of this limit is equal to 1 over natural constant E. So idea is very similar to the estimation of integral test, but our bound is easier than integral test. So we can only just look at this n+1 term, the estimate the nth partial sum, the error for nth partial sum. We have one more explanation in this section. Oh, any question about this example?
Could you just explain how you got that B7 and B6 are supposed to be the two that you use again?
So we need to correct to 3 decimal place. So you need some number which is between 0.001 and some number less than 0.001. And it shows that this number is good enough to estimate your sum up to 3 decimal numbers. It's better if you do some more partial sum, but you don't need to for this correction. I mean, correct to 3 decimal place.
How do you know it's a 1/e? Like, how can you get the result 1/e?
You'll see later. Yeah,
I'll see
you're
it.
not ready yet to show. Other questions? So series AN is called absolutely convergent. If the series of absolute value converges, in treatment, so if you take the absolute value for this AN and if the series of these absolute values converges, then you say that the original series is absolutely convergent. So, finally, you see see this alternating series of n squared, then by alternating series test, it converges. And if you take absolute value of this series, then 1/n squared, and it converges by p-series test. Converges. So means is sequence is convergent and absolutely convergent. This is a review of what we done. Now let us consider difference. So alternate alternating harmonic series. 1 minus hat plus a third minus quarter. And we showed that by alternating series paths, it converges. But if you take absolute value, then you get harmonic sum. And again, by p-series test, and p is equal to 1 in this case, it diverges. So this series is convergence, but not absolutely convergence. It's convergence, but not absolutely convergence. There's one more definition that a series is conditionally convergent if it is convergent but not absolutely convergent.
Excuse me. Excuse me. When we say harmonic series, it could be a alternating series, right? Like it can be like changing the sign, right?
Yeah. So if your series consists of all positive numbers, then this convergence is equivalent to absolutely convergence, because if you take absolute value, it's still a positive number. But if your series mix with positive numbers and negative numbers, then this absolute convergence is stronger, different from the convergence in usual sense. And maybe you already noticed that absolute convergence is stronger than convergence without convergence. If a series is absolutely convergent, then it is convergent. So this is another way to show the convergence.
What do you mean
Suffered
conditional?
that,
Conditional?
showing absolute convergence is easier than the convergence of series.
What does that mean? Conditionally convergent? Like,
So this alternating harmonic series is an example of conditional convergence. So this series itself is convergence, but if you take absolute values, then this series doesn't converge.
okay, this is the mean conditionally.
Yeah,
Okay.
like conditional convergence in a series is convergence, but if you take absolute values, then it doesn't converge.
Okay.
You can actually prove this theorem. Since absolute value of an is an if an is non-negative, and minus an if an is negative, we have 0 is less than or equal to an plus absolute value of an and this is less than equal to 2 times absolute value of an. So if an is negative, then this term in the middle is 0. And if it's positive or 0, then it's positive and this is 2 times over there. So we always have this inequality. Then we can use the comparison test here. For the comparison test, since we assume that an is absolutely convergent and this one is 2 times of absolute value of an, so it's also convergent. So we know this series an plus absolute value of an converge. Then this original series is an plus absolute value an minus absolute value of an. And we know that these two series converge, so we can split to subtraction of two series. And yeah, and it converges because each series converges. Each series converges. So converge. So yeah, this is a proof of the theorem that if our series is absolutely convergent, then the original series is convergent as well. So let us see an application of this theorem. So sometimes the convergence of absolute values series is easier than original series. From n is equal to 1 to infinity of cosine n over n squared. It's cosine 1 over 1 squared plus cosine 2 over 2 squared plus. And it is not an alternating series because the sign of cosine n is not alternating. It could be positive or it could be negative, but it's not positive, negative, positive, negative. It's more disordered. Determine whether this series converge or diverge. So the solution is if you take absolute value of this sequence, then it is less than or equal to 1 over n squared. Yeah, right. Because absolute value of a cosine trigonometric function is always less than or equal to 1. And we know that 1 over, and by comparison test, this series is absolutely convergent. right here. The comparison test. Series is find n over n squared is absolutely convergent. And you abbreviate absolutely by ABS.
Therefore,
So by the theorem I just erased,
the series convergent.
is series is also convergent. Because we have many criterions for the convergence and divergence of positive series, like P series, or we have integral tests. All of these tests works for positive series. So there are some tools to show the absolute convergence for some series. And here we use the criterion for a P series test.
P series.
Okay, there are many new things today. There's one more test. This is the last one. The ratio test. If this is just general series of AN, the limit of the absolute value of the ratio of adjacent terms, AN plus 1 over AN, is equal to L, which is less than 1, and the series AN is absolutely convergence. Is absolutely convergent, and therefore convergent. So, second is if the limit of this absolute value of the ratio of adjacent terms is convergence and greater than 1, then 4. The limit is infinity. Then the series diverge. And 3. If this limit of the absolute value of adjacent ratio is equal to 1, then the ratio test is inconclusive. By inconclusive, I mean you can't tell the convergence or divergence from only from this property. So this is almost the same as the geometric series.
Oh yeah.
Because this tells you that it's not exactly the geometric series, but if you compare the adjacent terms, then they are almost multiplied by L, which is smaller than 1. So if you see the series of absolute values, then it behaves like geometric series whose common ratio is large L. So if your common ratio is less than 1, then we know that geometric series is
Correct.
And if your common ratio is greater than 1, yeah, then it diverges. But for the geometric series, if your common ratio is equal to 1, then we know it diverges.
Diverges.
But since it's not exactly the geometric series, there are some issues when this limit of ratio is exactly equal to 1. Let's see the examples for the third case.
So if the series is a geometric series, we can say if equal to 1, then we diverge, right?
Yeah.
Okay.
For geometric series. So here further discussion of this third case. The following example. Sorry, which one is almost tired. So you see sum of 1 over n squared. Then you actually, yeah, we can use many tests to show the convergence of this. But let us now use the ratio test.
We can use P series.
The limit of the ratio is 1 over n plus 1 squared over 1 over n squared, which is n squared over n plus 1 squared, and it's not hard to show this limit is equal to 1. So by the ratio test, you can't say anything about the convergence and divergence of this series. But we know that it's divergent. It converges.
Because P series?
Yeah, P series we use this integral test or this P series. But the ratio test, but not by the ratio test. Let's see 1 over n. For a similar reason, the limit of the ratio of Jason's terms is the limit of n over n plus 1, which is equal to 1, and we know that it diverges. But again, not by the ratio test. So these two examples tells you that the limit is equal to 1, but it could be convergent and it could be divergent. So yeah. Shows that the limit equal to 1 cannot say convergence and divergence of a series. Example 8 has a series -1 to the n times n cube over 3 to the n for absolute convergence. Um,
Limit.
So roughly speaking, the numerator is polynomial and denominator is power or geometric series, geometric sequence or exponential.
Exponential, yeah.
And I told you that exponential always win the polynomial eventually.
Guess
So
zero.
if you compare these two, then you can consider them as almost geometric series. So, but it's not exactly a geometric series, so you can't apply the criterion for geometric series. So it's kind of geometric series and some error term is added. In this case, you can use ratio test. Ratio test is suitable for something like geometric series, but some error term is added so that it cannot be seen as exactly geometric series.
But the question will tell us which method we're gonna use, right? Like this question tell us like test with absolute convergence.
Questions are usually not that kind to provide you what test you use, but I'm telling you about how to
Okay.
choose some tests you can use. But yeah, so let us use the ratio test. An plus 1 over an is, since we have absolute values, so let us just ignore these signs. And we have n plus 1
N plus
cube
1.
over 3 to the plus 1 over an is n cube over 3n. Then if we see this fraction of fractions, then we can simplify to n plus 1 over n cube times 1 over 3. And this term goes to 1, so we have third. And this is equal, this is less than 1.
Can you go more detail of the second step?
This one.
Yeah. How do you get that number?
Okay, let us write one more step here. This is n plus 1 cube over 3 to n plus 1 times 3 to the n over n cube.
Like flip, right? Flip.
Yeah,
Right.
so denominator is flipped
Oh.
when you change the division to multiplication. Or remember A over B over C over D is inner products go to denominator and outer products go to numerator. But more precise way is this is equal to A over B minus C over D is equal to A over B, and you flip this fraction.
Oh.
So by the ratio test is absolutely convergent. Ratio test is absolutely convergent. Example 9 test the convergence of the following series n to the n over n factorial. So this again is not a good example because it has easier solution than using the ratio test, but let's use the ratio test because we can practice this ratio test. The first solution is ratio test. The limit of an plus 1 over an is n plus 1 to n plus 1 over n plus 1 factorial over n to n over n factorial. So now we again have fraction of fractions. Then we have n plus 1 to n plus 1 over n to n. And we flip the denominators n factorial over n plus 1 factorial. And let us borrow 1 n plus 1 from this power and change it to n plus 1 factorial here. So n plus 1 to n over n to n times, since we borrow the n plus 1 and plus single n plus 1 from this power, we have n plus 1 factorial over n plus 1 factorial. Is it okay? Then you can cancel these two. And get limit of n plus 1 to the n over n to the n. And should be able to calculate this limit. So what is you combine these two powers, so single power, and you have 1 over 1 plus n to n. And this is a natural constant e. Is 2.7 something is greater than 1. So by ratio test, since this limit is strictly greater than 1, we can conclude that it diverges. Ratio test.
How do we get an E?
But let us think about this sequence. So if you take out the shorter curve, it's n to n over n factorial. This numerator is multiplication of n by n times.
Is
And
a
the
greater.
denominator is 1 times 2 times 3 times of n. So
Is a greater than
this
1.
one is this general term is infinity. So yeah, diverges again. Because if this general term converges, so if it series converges, then the limit of sequence has to be 0. So I mean, they are the textbook quality. You should use the ratio test for this series. There's easier way to show the divergence of this series.
So in our test, either one we will be work, right? As long as we got the answer.
Yeah,
Okay.
you can use any test to show convergence and divergence.
So how do you get the E?
You see?
Yeah.
Oh, this is formula that you you have to remember.
It's formula.
I'm not sure you should learn about it a lot. Class before this course should be learn a capital B or A. So it's like 1/x, 3x, there, x and b. Okay, just plug in the figures. Okay, I think today's lecture was a little bit fast, so next time we will go over some exercise problems for section 8.3 and